Hello my people, hope you're doing okay. This will be the third video on trig integrals. Um, and let's go ahead and start with a cotangent cosecant problem. Now remember, just like secant and tangent, cosecant and cotangent are related both by derivative and by Pythagorean. But the thing that needs to be remembered about these is the derivatives of cofunctions are negative. And so we got to be careful with the negatives as those sort of swirl around with the rest of what's going on. But just if I had tangent cubed and secant, I would basically want to pull out a tangent secant because that would leave, the only thing that would be left over would be a square such that I could use a Pythagorean. So let me show you what I mean. This is going to be cotangent squared x and then cosecant x cotangent x dx. And you're thinking to yourself, yeah, but if cotangent's my u, then that's not my du. Okay, well spotted. But the thing is that cotangent squared can easily be turned into cosecant squared minus 1, right? For those of you that don't remember, cotangent squared x is equal to cosecant squared x minus 1. But I also know that this needs a negative right here. So could I go ahead and basically instead substitute in 1 minus cosecant squared x, and in doing so, basically turn this negative as well? And the answer is yes. That's entirely the reason why I'm doing it. So, I mean, you can do this in 2 steps. I'm just choosing to do it in 1, and you get negative cosecant x cotangent x dx. Now, this right here is obviously your du. This is 1 minus u squared. Now that you have that, basically, you need to remember that this doesn't become x because you actually are negative cosecant x cotangent x dx, right? If you were to distribute this across and then minus cosecant squared x, and I don't want to cancel out these negatives because the negative is an important part of the du. So really what you have here is this amounts to the integral of du, and this right here amounts to u squared du. And it's a little harder to see when you got all those negatives sort of swirling around in there, and you're trying to keep the negatives so that you can have an appropriate du and not resolve the negatives, because at this point, basically leaving something unsimplified for a strategic purpose oftentimes makes certain calculus students go crazy. But that is indeed what we have to do. And of course, this is the recognizable derivative of cosecant, so that its integral is cosecant. And then this is just u squared du, so it winds up being 1/3 u cubed plus c. And that is how we integrate that one. And it's very, very similar to the secant and tangent ones because their behaviors are really, really similar, except for the negatives. So you just have to be careful of the negatives. All right, let's go ahead and play around with this one. What do you say? Okay, now, remember that this is going to be similar to this one, okay? And because they're both even, just like on this one, I don't want to pull out a secant tangent. What I want to do is I want to pull out a cosecant squared. So cotangent to the 6th x times cosecant squared x times cosecant squared x dx. Now that's really close to being my du. If I just want to pop a negative out in front right here just to go ahead and make my du. But I know that negative cosecant squared x is a derivative of cotangent. But my cosecants that are left over, right, are still basically capable of being turned, all of them, into cotangent because there's an even number of them. And so let's do negative, and we have cotangent to the 6th x, and the cosecant is going to be cotangent squared plus 1. Okay, and if we go ahead and distribute, we're going to get cotangent to the 8th x plus cotangent to the 6th x, and then negative cosecant squared x dx. That basically winds up being, right here, this is my u to the 8th. Right here, this is my u to the 6th. And right here, this whole thing is my du. So I can just go ahead and integrate term by term, and I get negative 1/9 cotangent to the 9th x minus 1/7 cotangent to the 7th x, being mindful to distribute this negative to both of these terms, right, plus c. And like I said, except for keeping track of that negative, this behaves exactly like a secant and tangent problem. So I don't want to belabor the cosecant and cotangent variety of problems simply because we've already done their cousin, right? The secant and tangent ones. I want to move on to ones that are, require just a little bit more thought than the ones that have been sort of presented to us in a straightforward way so far. So this one right here, I'll be honest, all that notation kind of got me like bleary-eyed, and I made a mistake, and I read that as both of them being to the 5th power, and then I tried to integrate it. It was messy, let me tell you. But in this particular one, we don't have that. We don't have it to the 5th. We have sine to the 5th, and we have cosine. We have cosine squared. So what happens here is just like the 2x is there, but oftentimes the 2x is there just to distract us, okay? And so, whatever you can do to not let it distract you, this is going to be of the same strategy, even though the 2x obviously impacts the answer. It's the same strategy as that, right? And in this one, we notice that sine is raised to an odd power, and therefore it's the one that's going to leave sort of the residue behind to be combined with the dx. Well, the same is true right here. Okay, so what we're going to do is let's go ahead and write that cosine squared 2x first. Then let's do the 1 minus sine squared 2x. Well, that will be for 2 of them, but if I want it to be for 4 of them, I'm going to have to go ahead and square that bad boy. And what's left over is the sine of 2x dx. Well, let's go ahead and oh, this is supposed to be cosine. That's what's messing me up. Okay, that's supposed to be 1 minus cosine squared. Otherwise, I just changed sine squared into 1 minus sine squared. So what I need to do is let's go ahead and multiply all of that out. And the great thing about a difference when it's squared is it doesn't matter what order you do it in. And so you get cosine squared 2x, and then when I square this, I can basically do it in descending order. It doesn't matter. 2 cosine squared 2x plus 1, and then, of course, sine 2x dx. Once I actually distribute that cosine across, and I'm going to get cosine to the 6th 2x minus 2 cosine to the 4th 2x plus cosine squared 2x. Now I have u to the 6th minus 2u to the 4th plus u squared. My u is cosine of 2x. So not only am I going to need a negative in here to round out my du, I need a negative 2. All right, and if I put a negative 2 right here, I got to plop a negative 1/2 out in front, lest I change the value. Okay? Because if u is cosine 2x, then du is negative sine 2x times 2, so negative 2 sine 2x dx. Okay. Well, all this means is if this is u to the 6th, then I have negative 1/2 times 1/7 cosine to the 2x, right? Because this winds up being, basically the 2 that belongs here is already over here for each one of the terms. 7 2x minus, this is going to be 2/5 cosine to the 5th 2x plus 1/3 cosine cubed 2x, and then plus c. And of course you can, I ran out of room a little bit, but you can distribute that negative 1/2. That's not a big deal. But you see the fact that the strategy, despite the fact that the 2x was there and has the potential to distract us, the strategy was exactly the same as the single angle that corresponds to it with the same exponents. Now when we get something like this, we notice that that's not sine and cosine. That's also not tangent and secant. Or is it? And the answer is yes, it is. Okay. What happens here is sine needs to become tangent, and in order to do that, it needs to borrow a secant from this secant to the 7th. So what happens here is when it borrows that, it becomes tangent x, and that secant is now secant to the 6th x. Well, tangent obviously cannot be changed, but it can be pulled out as part of my du. And now I have u to the 5th du. And that means I have 1/6 u to the 6th plus c. So that one, despite the fact that it started out kind of looking weird, just took one step, and then it actually wound up being pretty straightforward. Okay. The same thing for this next one. We have sine over cosine squared, and we've been used to dealing with sine and cosine as long as they both had positive exponents, but that cosine squared is in the denominator, so that's really cosine to the -2. But just like the last one, if I stop and think for a moment, I can recognize the fact that that can be transformed into sine x over cosine x times 1 over cosine x dx, which, if you pull it apart like that into strategic factors, that becomes, and of course I should have put the 1 over cosine first, so it can be secant tangent, and that winds up being really, really easy. The derivative, secant tangent is the recognizable derivative of secant. And boom. Okay, let's see, how much time? Okay, let's do one more, and then I think it's good to basically put a break in the videos before we start on the definite integrals. This last one right here actually doesn't need to change the form at all. Well, I mean, it might be helpful to actually think of this like that, right? Pull it out of the lazy man's notation and actually make it explicit that what we're talking about is u to the 1/2 du, and that becomes 2/3 tangent to the 3/2 x plus c. And that one actually, while the fractional exponents of trig functions sometimes make some people nervous, it really shouldn't. That one actually winds up being pretty straightforward. That brings us to the end of the indefinite integrals. We're going to do some definite integrals, and then we're going to get into the use of some product to sum identities for ones that take a different form. Whereas instead of cosine and sine having different exponents, you have a product of sine and cosine that have different angle measurement expressions. And that'll be and we did one or two of those in class, so those shouldn't come as a surprise. But that's what's coming down the pike in the next couple of videos. As always, if you have any questions, please shoot me an email. Bye.